Hello and welcome. My name is Ben Consalvo and I'm excited to present some of my work on combining physics and deep learning to automatically pick first breaks in the Permian Basin. So a little bit about me before I dive straight into the talk. I worked on this topic while I was working in data science and geophysics research at Fairfield Geotechnologies in Houston, Texas, mostly in 2020. I now work as a senior AI engineer at a cybersecurity firm called Zavilo, working mostly on anti-phishing solutions with computer vision. I'm so glad to present this work and hope you enjoy hearing it also. Alright, so here's a brief outline of my talk. Start with an introduction discussing the time-consuming nature of first break picking. We'll look at the methods of physics-based tomography and deep learning very briefly, and then we'll go through the field data from the Permian Basin. We'll then look at some of the results comparing traditional to deep learning, traditional methods to deep learning methods for picking first breaks, and then I'll end with some conclusions, freeing up some of our time using deep learning. Alright, so here I wanted to show you a sample shot gather for some of you who might not be as familiar with first breaks or seismic data. So first breaks represent the energy at the two-way time it takes for a sound wave to travel from the source, like a vibroseismic truck, dynamite, or air gun, to the first refractor, often at the base of the weathering layer. So in terms of what that looks like, it's if we have our shot location here on the shot gather, then we have this in red, these first refracted arrivals, and this is just a sample shot just to show you this. There's some other arrivals I've pointed out on here as well, like ground roll and reflected arrivals, but the ones that we're concerned with are these red dots where we see the first refracted energy, the P-wave refractions. So if you're interested in this talk, it's likely that you're either interested in deep learning or in the first break picking problem. Why do we pick first breaks in the first place? Picking first breaks is a crucial building block for the rest of seismic imaging, and they also directly serve as input to producing the first velocity models to use in depth imaging, and for later subsequent drilling for oil and gas. If you already know anything about picking first breaks, you know that it is a very time-consuming task, even with some assist from automation and software packages. Picking first breaks can take weeks or months for one seismic survey, especially now with these dense 3D seismic surveys reaching into the billions of traces. I can attest to the time-consuming nature of this task, as I personally spent weeks picking first breaks on a 2D seismic survey from Eastern Ohio during my master's thesis, and that was just a 2D survey. So complicated geology and varying velocities in the subsurface makes traditional first break picking approaches difficult. The best approach we found was iterating between a traditional physics-based tomography for getting better velocities and a deep learning approach. I want to show you a big picture overview of the two methods we are comparing in this paper, and then go into a bit more detail on the methods. So the end goal of either method is to produce high quality first break picks that match with the onset of the first arrival. So I'm comparing a more traditional auto picker approach, which I'm showing as this top flow, with the deep learning auto picker and showing the bottom here. So both start out as needing to have a normal move out picked sparsely across the survey. The first method shown on top is a more traditional approach of auto picking, where we iterate between something called the threshold auto picker, and that uses time windows and energy thresholds to pick first breaks, and using this first break travel time tomography to refine the velocities. And then the second method is using deep learning to automatically pick the first breaks, and letting a trained neural network do that and then again using tomography to update the normal move-out velocities. And then I'm just showing here an example of two outputs from either of these, which I'll show these again near the end of the presentation and go through them in detail. Alright, so each of these two methods requires input move-out corrected seismic gathers, but the deep learning approach does not need perfectly flat seismic gathers for it to work, and they can be quite sparse across the survey. So manually picking sparse move-out trends only takes around 30 minutes or less for a large, in our case 265 square mile survey. We used the same move-out trend as input for both methods to make sure we were comparing apples to apples. If the move-out were always the same across the survey and the Earth were homogeneous and flat everywhere, we could just pick the move-out and draw a straight line for all first breaks and be done. So we could just go, okay, yep, it's a perfectly flat line, and we would be done. But the Earth is heterogeneous with varying velocity structure, and it is often much more difficult to pick move-out trends, unlike the one that I'm showing here. However, for the purpose of this work, the deep learning model only needs a very rough, sparse NMO trend picked, or move-out trend picked. In order to avoid manually picking first breaks on every trace in a seismic survey, automated approaches have been introduced to simplify the process. And so here I'm going to be comparing this threshold approach with a deep learning approach. So the threshold auto picker is, like I mentioned, one of these approaches, and it has been widely used in the seismic industry for decades. It is based on this Coppens 1985 paper, and it uses time windows and user-defined energy thresholds to pick first breaks. The threshold approach works well when the signal-to-noise ratio is relatively high, but tends to fail in the presence of noise. The threshold values can be adjusted manually to create slightly different pickers. However, the result is that the threshold approach only works well for certain portions of the survey and tends to fail in other portions, particularly when we have noise or complex geology. Now, concerning the deep learning approach, if you're a deep learning geek like me, you might be sad that I don't spend more time talking about the training, but what I'm trying to emphasize and go over here are the results of using deep learning rather than bogging us down in the details of the neural network architectures. Briefly, I will give a description. So convolutional neural networks have recently achieved state-of-the-art results in many image classification tasks and object detection tasks, even in the presence of noise. Deep trace is a deep learning approach that uses a combination of unsupervised learning and supervised learning from human-labeled first breaks in a variety of contexts. Models are trained directly on raw seismic data, as well as data that have been flattened using human-defined move-out trends. We regularize deep trace and improve its generalization ability by training it on seismic data on a seismic data reconstruction task, which is a form of unsupervised learning. During training, we mask part of this input seismic data and ask deep trace to reconstruct the missing input. This actually allows us to train on seismic data even where picks are missing. So long and short of it is that the deep learning approach, unlike the threshold approach, actually does perform well in the presence of noise and even in areas of complex geology and varied velocities. Originally, we had tried using only deep learning to predict first breaks without the use of any physics-based tomography approaches. However, we found that combining the physics-based first break tomography with deep learning resulted in the most accurate first break picks, going back and forth between this deep learning and refining the move-out velocity with travel time tomography. The same parameters were kept for tomography, whether using the input of the deep learning auto picker or the threshold auto picker, to make sure we had an equal comparison between auto picking methods. So the primary physical model used in this study is called auto-adaptive node spacing, or AANS, a tomographic algorithm that improves on the traditional iconal travel time solvers, originally with Vidal in 1988 and 1990. The subsurface model consists of a 3D array of node locations where the vertical spacing can differ from the horizontal node spacing. Ultimately, the slowness values at each node are chosen to minimize a least squared error objective function for travel times. So moving on to field data, the data that we used in this study was a 3D seismic survey conducted over 265 square miles on the west side of Texas, USA, in the Permian Basin for the purpose of oil and gas exploration. As I'm pointing out on this slide, there are 200, like I said, it's 265 square miles. It contains approximately 33 million traces with 41,455 unique shot locations and 48,586 unique receiver locations. The source and the receiver station spacings were both 165 feet apart, approximately. The figure I'm showing here is an elevation map of the survey, and the data points, they all come from the receiver stations. The F that I'm showing here denotes a fill zone area. This fill zone in particular poses a serious seismic imaging problem, and without the proper first breaks and recovered velocities here, there is not hope of recovering a depth image to be able to drill for oil and gas in this area. The dotted black line shows below it, so this line here I'm showing, is the location of a 2D velocity model cross-section, which we will see on the next slide. This area of velocity is particularly challenging for most autopickers to get the first break picks correct, and usually requires a lot of manual intervention. So here I'm showing 2D velocity profiles over this fill zone for the initial velocity and the final velocity. The starting velocity model is shown on top, so the purple, mostly purple, and it's pretty slow at around 2,500 feet per second, generated from our very first rough move-out velocity picks. The final velocity models from both the threshold and the deep trace approaches are shown here also. So here, yeah, B is the threshold and C deep trace. The black curve, it's kind of hard to see, but it's a curve that kind of looks, like that. That is actually the ray penetration extents. What we can see here is that both approaches from the threshold and deep trace did produce similar looking velocities, but the threshold approach appears to be less smooth and more looks like stair steps in places. This behavior is likely due to the fact that many of the picks were placed at very different times, even on, the stair steps like this. The behavior is likely due because the picks were placed at very different times, even on adjacent traces when they were noisy and they weren't very accurate. In general, the deep trace produced slightly slower velocities, so we can see more of the yellow here than the threshold. It generally produced, slightly slower velocities. Overall, for the error, the threshold approach produced picks with an average error of 21 milliseconds, and this is the travel time tomography error, whereas the final model from the deep trace workflow produced picks with an average around 10 milliseconds, which is about half of the threshold approach. So the error is a measure between the forward modeled picks from the physics-based tomography and each respective autopicker. In theory, it would be helpful to compare picks to human picks, however, no such picks were available, and they would likely take over a month for one person to complete for the whole survey. These errors are therefore not the true error, as modeling errors will be reflected in this value. So here I'm comparing the results of the final first break picks between the more traditional threshold approach and the deep learning approach. On the right hand side, I'm showing the location of a survey map, and the black dots represent the shot location, which is here, and then the receiver locations, which are below it. This is an interesting area I noted earlier called the fill zone, which has particularly complicated velocities and is typically very difficult for autopickers to do well. When we look at the threshold approach on the top image, we can see on these purple dots that it does get some of the picks correct, especially with high signal to noise ratio, but in the presence of noise, This threshold picker picks first breaks all over the place. You can see some of them up here and up here. And they're not always even visible in this time window that I've selected here. The deep trace workflow not only produces a flatter move out correction for the same area, but also produces much higher quality, consistent first break picks, even in the challenging fill zone that we're in. Here's another such comparison, but this time more in the middle of the survey. Again, on the right, I'm showing a map view of the survey locations or the receiver positions. And so the shot again is here. It's kind of hard to see with the red there. And then the receivers are below it there. The results from the deep trace again illustrate the fact that even in the presence of noise, high quality picks can be obtained. The picks definitely are not perfect. You might spot some imperfections in the results, but they are more consistent and of higher quality than the traditional threshold approach. So I presented what I would humbly consider a successful approach of using a combination of deep learning and tomography to automatically pick first breaks. We were able to run the complete workflow in only 4 days on 33 million traces, but this could be reduced further with added CPU capacity. Our qualitative observations are that the deep learning workflow produced significantly better first breaks than the traditional threshold workflow. In order to produce satisfactory results using the threshold workflow, at least 3 additional weeks of manual intervention would likely be required. There is often this tension between near-surface geophysical modeling, between taking human time to manually produce high-quality picks and quickly producing lower-quality picks using automated methods. We find that the deep learning and physics workflow described in this paper resolves this tension, freeing human time that is normally spent picking to focus on more complex. This is normally spent, picking to more complex geophysical modeling tasks. We were especially pleased with the prediction results from deep trace, the generalization ability, given that only data from outside the survey were used during training. I want to thank you for taking the time to listening to my presentation. I hope you found it interesting and exciting. I am so looking forward to seeing where deep learning takes the oil and gas industry, and I would be happy to answer any questions, whether at the time of the presentation or later on. Thank you very much.